you're going to open up.
All right. Well, hello, everyone, and welcome to the Columbia Memorial Space Center. So glad to have all of you here today. And I noticed that our wonderful virtual background is not catching the full haircut there. So it's making me look a little more bald than usual. But hi, everyone. My name is Jared Head. I'm one of the activity specialists here at the Columbia Memorial Space Center, where we are Space Center Live as we play around with all this stuff. I've also got Rick, one of our I guess I call center managers here, something like the program managers, who's sort of been helping get all this going. And we wanted to do this Space Center Live because we know that everybody's sort of been inside and kind of not really been able to do much. And there's been a lot of science happening, and you may have some science questions. So we wanted to answer them. We wanted to still be sort of a source of answers and understanding for you, even though you may not be able to make it here with us today. Now, to kind of get started with what we're going to be talking about today, you may have heard recently that there is a discovery concerning Venus, the planet behind me right here. We're not actually at Venus, but if you were in orbit around Venus, it would look a little bit like that. And specifically a discovery about something that was entirely unexpected regarding Venus, which was the potentiality of life on Venus. Now, the study that came out did not say that there is life on Venus or that this is evidence of life at Venus. It simply was finding a gas that is a signature potentially of life. So there was a lot of sort of headlines about aliens on Venus and other things like that. And that's not true. That's not really what the study was about. The study was basically saying, hey, we found this gas that we usually only find, here on Earth because of life at Venus. And that's really, really weird. And we'll talk about that gas a little bit later as well, because I kind of want to give you a little bit of a rundown of how we've explored Venus. And let's go ahead, and I'm going to see if I can share my screen here for all of you as we work through this today. So you're having just as much of a learning experience as we are today with everything that we've got going on here with this. So bear with me for just a second. All right, excellent. So we have got Venus right here, which I'm trying to pull up so everybody, can take a good look at it real quick. And let's go ahead. We're going to share that right there. As we can see, the planet Venus fully enshrouded in clouds. So it's a pretty tough place to actually end up studying, simply because we really don't have a good view of the surface below it, because Venus's atmosphere is very, very thick. And Venus was one of the first planets looked at. Galileo Galilei looked through his telescope in Italy in the early 1600s and saw that Venus didn't stay the same shape, that it was actually like our moon. It had phases. And he went out and he told everybody about that, and he got into a lot of trouble because of that as well. There were some other things too involving Galileo getting in trouble, but you can read the book on that a little bit later with that there. And then throughout the 17th and 18th century and 19th century, scientists continued to study Venus as best they could through the telescopes that they had. And there was wild speculation. They realized that Venus was just about the same size as the Earth, and then it had an atmosphere like the Earth does. So there was sort of this idea that, it's like a tropical paradise. And there were even some ideas like, maybe there's oceans of carbonated water, or even oceans of petroleum, gasoline sitting there just waiting for some sort of heavenly enjoyment, like I'm gonna go down to the beach and enjoy myself, on Venus. Turns out that's not true. When we started looking at Venus with radio telescopes in the 1950s, we found that it was not a particularly great place. It's pretty hot there. The surface gets up to about 860 degrees Fahrenheit. So that's a little hot. That's hot enough to melt lead. And in addition to that, we also know that Venus's atmosphere is made of carbon dioxide. You and I cannot breathe carbon dioxide and live. That's very, very bad for us. In addition to that, Venus's atmosphere at the surface is really thick. It's 90 times thicker than what we have at sea level here on Earth. So that means that if you were standing on the surface of Venus, the air pressure from the atmosphere would be the equivalent of standing landing under 3,000 feet of water. So that is a really high pressure. And in addition to that, there are clouds of sulfuric acid and droplets of it. Don't know if it rains sulfuric acid. The jury's still out on that, but we do know that the clouds you're seeing there are mostly sulfuric acid droplets, so probably not the best clouds to fly anything into. But of course, even though we found out that Venus is a deadly place that absolutely you should not ever go to, scientists, they decided they wanted to go and study Venus. And in fact, Venus was one of the first planets that we flew a spacecraft past, which was Mariner 2 that JPL flew in 1962. And then the United States sort of looked at the other planets out there and started aiming towards Mars. But the Soviet Union really got on a kick with Venus, and they ended up starting to send a multitude of probes there. And really one of the great programs that they did was the Veneer program. And those Veneer Landers were very, very tough. I'm pulling up a image of one right now so you all can get a look at it. They were essentially tanks that the Soviet Union built to survive the surface of Venus as best as possible. But of course, you know, it's really tough to build something that can actually work in that kind of an environment. So they did their best, and some of those Veneer Landers actually ended up making it to the surface and surviving, which is pretty amazing that they were able to do that. So just trying to get this open for you here so that way we can get a really nice good look at that. All right, very good. I think we got it here. And now we'll go into here. Those Veneer Landers, because of their design, they were able to work very, very effectively on the surface with that there. And, you know, kind of do everything that they needed to do and take some samples on the way down of the atmosphere and other things like that. And we'll take a look at this here. All right, should be getting it now. We'll get that. And yeah, pretty tough looking lander there. Hopefully you can see the lander coming through. I'm not getting any indication over here that it's working, but they are some very tough spacecraft because they had to survive that environment. They had to survive the extreme temperatures. They had to survive the conditions of pressure and the corrosive atmosphere coming down. And most of them lasted about 30 to 45 minutes on the surface. One of them ended up lasting just a little over 2 hours on the surface. And they actually gave us our first images of the surface of Venus as well, which was showing sort of this scorching place. Definitely not a place that you or I would want to end up in here. So look at this wonderful, absolutely amazing view of the surface of Venus here. So you can see that Venus has rocks like we would find at Hawaii, which are sort of near the volcanoes there. And there's nothing really there other than rocks, right? So it's not exactly what I would call the friendliest of places to want to go visit. And at the bottom there, we can actually see a part of the lander, of the Veneer lander, that sort of ring right there was like a crush core. So when it would land on the surface, it would sort of crush into that a little bit, crumple it a little bit, because the Veneer Landers, they used parachutes to slow down a little bit, but then once they got into the thick atmosphere, you actually didn't need a parachute anymore because the atmosphere was so thick, you could just pull on it using like a big sort of metal umbrella kind of shape to the top of them, and that was it. And the surface of Venus overall is not a very a fun place, I guess, that most people would look at. It's very much a very dry, rocky desert kind of area with that very yellowish color in the sky. Not particularly fun with that there. And there's some Veneer Landers, the Veneer Lander design there for you, just so you can kind of get an idea of what they look like. If you went up to one, you'd stand just about as tall as it. It had cameras, it had sensors to sniff the atmosphere, temperature, and it had a little sort of drill that could figure out what the rocks were made out of, and that's how we know that the rocks are very similar to what we have here on Earth in Hawaii. So very, very cool stuff that they were able to pull off with that. Now, it wasn't really until we got into the late 70s when the United States decided to kind of bounce back and take a look at what was going on there. And that would be with the Pioneer Venus multi-probe mission. This was a very interesting mission because it would use a orbiter with several landers in there. And those landers were attached to a second probe that was actually launched. So it was two probes, one that had 4 landers attached, another that had the orbiter, like we see right here. And those 4 landers are the only vehicles that the United States has sent into the atmosphere of Venus. And this was back in 1978. And those atmospheric probes were not designed to survive, but one of them made it to the surface, and it worked on the surface for about 45 minutes. So we essentially in the United States accidentally landed on Venus in the 70s. And the Pioneer Venus probe, the orbiter, actually worked until 1992. So we got a lot of data from it using radar and other things to study Venus. And then came a spacecraft called Magellan. And what Magellan did, it was a very special spacecraft because it had a radar that would bounce down to the surface of Venus and then listen to the return. And from that, it was able to get even better radar images of the surface of Venus. And that's where we get those really cool ones from. So we do have another spacecraft in orbit around Venus right now called Akatsuki, which is sent by the Japanese Aerospace Exploration Agency. And that is a mission that is studying the atmosphere of Venus. So kind of looking at where we're going to be looking and talking about the potentiality for life on Venus. And in fact, that study was done by a group at Cambridge University and MIT working together. And they were working very hard to develop a proposal that would allow them to use this telescope, which is the James Maxwell Clerk telescope, up on top of Mauna Kea in Hawaii. So if you become an astronomer, you get to go to places like Hawaii for work. So I know I don't get to go to Hawaii for work, that's for sure. I get to come here in Downey, wonderful, beautiful Downey. This telescope uses what's called microwaves. So you may be familiar with microwaves, is what you use to like cook your Easy Mac or a Hot Pocket or something. But in astronomy, we use microwaves called submillimeter arrays and other stuff, other fun technical terms like that. But they proposed, because if you want to do a study, you have to write a proposal for telescope time, and they proposed to use this telescope, and their proposal was rejected. And they said, okay, well, okay, we'll do some better models. So they made some models. They ran some computer simulations that showed, the potentiality for this gas called phosphine to be at Venus. So what's so special about phosphine? Because we at that time, we knew that 3 planets had phosphine gas in their atmospheres. We know Earth, Jupiter, and Saturn had phosphine gas in their atmospheres. Well, Jupiter and Saturn, very difficult to make a good argument for life there. So kind of interactions of hydrogen, the gas hydrogen at lower levels in the atmospheres, are thought to make that phosphine, although now with this Venus study, it actually is starting to get a little bit of questioning back at that. And here on Earth, we know that phosphine comes from natural sources, biological sources, a little bacteria. Basically, I guess a good way to phrase it would be pooping out phosphine gas. I don't really know how to phrase it any better than that. Excreting phosphine gas. There we go. And that getting out. And we don't find processes involving rocks, like geological processes or volcanic or seismological or other things like that. So it's it was a sort of a marker for potentially how to study exoplanets in the future, because when we start to look at exoplanets and we look at their atmospheres, we're going to want to know, are the signatures of life in this atmosphere? Do we have things like water vapor? Do we have things like potentially chlorophyll? Do we have things like phosphine? And we wanted to see sort of, what it would take to detect those and whether it would actually be good detection or not. So that team from MIT and Cambridge basically threw a challenge flag at the rejection of their study. They said that we don't think that your rejection was a fair one. And the telescope team looked back at it and they said, oh, you know what? Actually, this is a pretty good question to ask. So they gave them the time, and telescope time on a telescope does not guarantee that you're actually going to get the data that you need. Everything has to go right. You have to have the right atmospheric conditions. You have to have the right viewing conditions from your target and other things like that. And they figured that this phosphine would appear in a certain part of Venus's atmosphere as well. It would be sort of in the mid-latitudes, kind of where we're at here in Los Angeles on Earth. And they took in the data and they took it back and they crunched it a little bit. And lo and behold, they found phosphine. And they found it exactly where they were expecting it to be, in the mid-latitude of Venus's atmosphere. So very surprising with them then. So what do you do when you get your data and you get confirmed data? Well, you do exactly what you're supposed to do when you confirm your data, which is you then take it and you do everything you can to try to prove yourself wrong, because that's how science works. It's not a sure bet. You have to make sure that all of your possible wrongs are corrected, and or all of your possible wrongs are right, if you will. And they did, and they found out that they couldn't explain it. So they went to another telescope called ALMA, the Atacama Large Millimeter Array, which is actually a much more powerful sub-millimeter telescope than the Maxwell Clerk telescope is, but it is a bunch of little itty bitty telescopes all together. And what they do is they look as a team of telescopes. And let's go ahead and take a look at them here. They're in the Atacama Desert down in South America. And by the way, just to remind everybody, if you have any questions, feel free to ask. This is Space Center Live. We are legitimately live right now. So if you ask a question, we'll give you an answer. And if we don't know the answer to it, I'll tell you I don't know. So I mean, hey, that's kind of nothing wrong with saying I don't know. So the Atacama Large Millimeter Array is a whole bunch of little itty bitty telescopes that they use computers to combine their signals together and make a image or take data from what would be equivalent to a telescope as big as the two smallest, furthest telescopes from each other. So imagine you've got all these little telescopes right here, and let's say that the two farthest away telescopes are a half mile away from each other. Well, all these little telescopes are maybe like 30 feet across at most. But when you combine all of their data together and you use the computers, it's what we call interferometry. So combining multiple telescopes together to make a view as one big telescope. So take all the data from these little 30-foot telescopes, and you're able to combine that data and get it as if a half-mile wide telescope was getting that data. So if you remember the image of the black hole that came out last year from the Event Horizon telescope, exact same thing, except the Event Horizon telescope was using telescopes across the entire Earth. So it was like making Earth the size of your radio telescope. But in this case, this is obviously not a Earth-sized telescope that they have right here. Would be nice to use that, but they used it, and they ended up continuing to confirm the data that they got from the James Maxwell Clerk telescope, which was very, very intriguing. And in addition to that, they found phosphine gas in concentrations that are actually too high for potential natural or geological processes to explain it. So that is what the study says. And the big thing, the big surprise, the reason that study was so exciting and so amazing and kind of blew everybody away is because you had institutions who were very well regarded. So groups like Cambridge University and MIT. This wasn't some like backwoods university that just published it in a magazine to try to get you to subscribe to it for a year. These were actual very well regarded institutions and people on these studies who have done a lifetime of specialization specifically in studying biology and phosphine. And they also brought on people who do planetary geology, atmospheric physics, and other things. So this wasn't just a narrow set of people. This was a broad range, a whole load of people, all the right people that you would need in order to actually say, yes, indeed, this is how this is. And the exciting part about it is that there are going to be two outcomes for this. Either it is potentially life that is making the phosphine, or it's a geological or atmospheric process that we don't understand. And what's so exciting about that is obviously life. I mean, that's really exciting, right? If you find life off of Earth, that suddenly, especially within our own solar system, that suddenly means that life is probably everywhere that you can conceivably think of. Life can adapt, evolve, and work in any environment that we could possibly throw it at. But if that's not true, if it's not life, if it turns out to be a geological process or a atmospheric process or something like that, that's something that we have completely no understanding of. That means that our ideas of planetary geology or planetary atmospherics and other things like that may be completely wrong. Like maybe this was a key that we completely missed at some point in the past, hundreds of years that we've been studying our solar system. So either way this goes, whether it is life or it isn't, is not only just a result, but a ground shaking result for the field that it's in. Obviously, a lot of us want it to be life, but I mean, myself as a scientist, I would be very excited either way it goes, simply because it builds upon the foundations of these fields and has the chance to potentially rattle them to their core. And that's what's so exciting about this, is that this really is a true type of cutting edge science. Now, the European Space Agency has a spacecraft on its way to Mercury called Bepi Colombo, and it actually just did a flyby of Venus a couple days ago. It has instruments on board that could allow it to detect phosphine. The problem is that this discovery was made too late for them to upload commands to the spacecraft to use those instruments to actively look for the phosphine. Another problem with this flyby as well was that they were about somewhere on the order of about 7,000 miles away from Venus as well. And that's really, really tough to try to get that data from instruments that, one, aren't looking for it, and two, are very far away from Venus. But a nice thing, in August of next year, Bepi Colombo will fly by Venus again for another gravity assist. This time it's only going to be 300 miles above the atmosphere, so it's going to be way closer. And we have plenty of time to actually have them aim the instruments down at Venus and figure out how to hunt for phosphine. And of course, there are, now that the paper is out, as how science goes, once you put a paper out there, you are basically releasing it and saying, hey, redo this, prove me wrong. And in science, prove me wrong is not a sort of like a smart aleck statement. It really is how things work. You want people to prove them wrong. And in fact, the MIT and Cambridge team have said that they can explain it. So if you can prove them wrong, they'll be very happy about that. And you don't hear that very often, which is always nice to. In science, you hear it pretty much all the time, but in other places, you don't really hear that very often. So it's really nice to hear that. But there are other teams, obviously, that now have the paper. They now have the methods that you can use for that, and they're going to go out and they're going to try to replicate the results, because in science, replication is key. So if these other groups go out and they find phosphine, oh, that's amazing. That's confirmation that it actually is there. And if Bepi Colombo flies by next year and finds phosphine, or if for some reason it's able to successfully find phosphine in the data that it just took a couple days ago as it flew past, holy moly, if you've got a spacecraft there confirming phosphine right there, then that's like, you really can't argue with that. It becomes very difficult to say that that's not a thing. So what do you do in the future, though? Because if we do find phosphine there, what are we going to do? Well, there are some ideas for missions that want to go to Venus. There are two. So NASA has several programs that fund missions. And there's one called the New Frontiers program. And there are currently 4 missions competing to be the next mission in that program. 2 of them will go to Venus. One will be a radar orbiter like Magellan was. So it will stay in orbit around Venus and take much better radar data than Magellan did. So to the point that if you were standing on the surface of Venus, the radar could actually detect you there. Magellan's not bad. We could detect our space center on the surface, but obviously we'd like to look at it a little bit better with that there. And the other one is a probe that'll actually drop into the atmosphere and sample it and take images all the way down and basically do what the Veneer probes did, but with modern instruments, not 1980s Soviet instruments. So it would be a much better data and much more data as well with that. But just a few weeks before the publishing of this paper, NASA did put out a plan that was done by JPL and the Glenn Research Center on the East Coast that showed what you would need need to do what we call a flagship mission to Venus. So basically, a flagship mission is the kind of mission that you send to a specific area to answer the biggest scientific questions about that planet. So for Saturn, we sent the flagship mission Cassini to it. For Jupiter, we sent Galileo. That was a flagship mission. There's also some flagship missions in orbit around the Earth, like the Hubble Space Telescope, or the upcoming James Webb Space Telescope as well. But for Venus, we've never had a flagship mission go there. They've always been very sort of, I don't want to call them low-ranking missions, because they are, every mission counts. But they are not, they're not the cream of the crop missions. They're not there to answer all those tough questions. So they looked at developing a flagship mission that would launch a orbiter that would also have 2 small satellites that it would release that would go into orbit on their own around Venus, as well a lander that would land on the surface of Venus, and one that they would design to last so it would last days on the surface instead of just like an hour or 2. And also what they call an aerobot. So basically dropping a balloon into Venus's atmosphere and having it hang out for about a year as it goes around Venus's atmosphere and samples all of those levels that they can. So that's very exciting. That's a mission that they estimated would be about $3 billion. So quite a bit of money, but you know, with phosphine coming into the fray here, and kind of this big surprise from Venus, you know, a planet that we were absolutely certain would have no chance of allowing life to survive on it, suddenly having a gas that we only know of here on Earth is made by life. Like, well, maybe we need to reconsider our exploration of Venus and like not ignore it anymore. You know, maybe we can give Mars like a 5-year break or something. With a little Mars vacation from that there. So it's a very exciting time with this study. Very exciting that we have missions on the cusp of potentially becoming a reality, and very exciting that we just so happen to have a very good group of NASA engineers and scientists look at the potential for a really big mission just before all of this info actually became a thing. So super exciting about that. And if you have any questions, you are welcome to ask them, because here at Space Center Live, we are all about answering your questions. You know, I guess the first question that I can answer is, no, we're not at Venus. We're here at Space Center today, although it's nice to have Venus behind us. And it's always interesting. I always find it interesting that the virtual backgrounds on Zoom cut off my mohawk that I have. So thanks for that, Zoom. I appreciate you showing me what I'm gonna look like in 20 years. So something like that. Yeah. So Venus is obviously a very difficult place to design things for. And when you hear about the problems of designing for Venus, you know, the surface is 860 degrees Fahrenheit day and night. That's the average temperature. It can get hotter in some areas. It can be a little bit cooler, relatively cooler. Like still like, you know, the tops of the mountains on Venus, it can be at about 700 degrees Fahrenheit. So I don't know if you want to go hit the slopes this winter at 700 degrees Fahrenheit. Actually, a really cool thing that they did find in the data from Magellan is that they found these areas on top of the mountains at Venus that are very reflective. They reflect radar very, very well. And they actually think that a metal called tellurium may be snow up on top of those mountains. So if you can imagine an area, a place that is so hot that metal is the snow on your mountains, Venus is wild, I tell you. That's a pretty cool thing. So how does life survive in a place like this? And I just realized I forgot to explain that. You know, how does life survive in a place that has these wild conditions, 860 degrees Fahrenheit, 90 times the pressure here at sea level at the surface, sulfuric acid and marine sulfuric acid and all that other good stuff, hydrogen sulfide and chlorine and other things in the atmosphere, stuff you don't want to breathe. How does it do it? Well, the place that they estimate the phosphine is at in Venus's atmosphere is actually high up in Venus's atmosphere. So Venus has a very thick atmosphere. It's roughly about 100 miles thick. That's very thick compared to the atmosphere that we have here on Earth. Here on Earth, our atmosphere only extends up about 62 miles, and then most of that is within essentially the bottom 10 miles there. And how does the life survive? Well, it's going to be higher up, and that higher up sort of atmosphere there has lower pressure. And in fact, I think it's at an area where you would have an equivalent pressure to what you have at sea level here on Earth. So that's pretty good, right? Excellent stuff with that there. And then in that area, what's the temperatures like? Well, it's actually room temperature at that altitude. So like we're very comfortably sitting in the Space Center here. It's very, very nice. So it's about the same temperature in that area. And is there sunlight? Yes, there is. So there is a potential source of energy because life needs life here on Earth, as we understand it, needs three things. You need carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So you need those 6 elements. You also need water, a source of water, liquid water, and then also a source of energy. And in case of here on Earth, most of that energy we get from the sun. So you have sunlight. So there you go. There's one of them. We definitely know that those 6 elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, are present in the atmosphere of Venus. And there are some studies coming from Akatsuki, that Japanese Aerospace Exploration Agency probe that's still in orbit around Venus right now, taking data. There is some data coming from it that says that there is potentially water vapor in the atmosphere of Venus there. So some very, very exciting things that we've got there, the potentiality for life. So holy moly, that area, suddenly it doesn't sound so wild that Venus may have life. It actually seems relatively possible. So we'll have to see. Again, science is one of those things where we're always moving forward with it, and it's often not as fast as a scientist would like to have it go, but hey, you kind of got to move at the speed that it lets you do it. So we're going to go ahead and wrap up our first episode of Space Center Live here today. So thank you so much for joining us all. Our next one will be sometime in mid-November. We're going to be talking about the International Space Station because we're going to be celebrating 20 years of a continuous human presence on board of the International Space Station. So we're going to talk a little bit about humans living in orbit over long periods of time. If you go to the space station, you spend about 6 months on board. There's also been some special studies like with Mark Kelly and a Russian cosmonaut where they spent just a little under a year, about 340 something days on orbit there, and saw how their bodies reacted to that, and doing a lot of great work there, because if you're going to Mars, it's at least 7 months to get there. So you're going to be in space for quite a while before you get there. So we're going to have to kind of figure out how that is. So we'll be talking about sort of like humans in space long-term, space stations as a whole, because space stations go all the way back to the 1970s with the Soviets starting that out. And we'll kind of talk about their evolution to the International Space Station, and also how you can see the International Space Station from your house, because you can, and we'll tell you how you're able to do it. So once again, thank you all for joining us for Space Center Live here at the Columbia Memorial Space Center. My name is Jared, and thank you so much for watching us. And until the next one, we'll see you.